morning. In the last lecture I was talking about catalyst characterization methods and we were talking the heat method. So, I said that you can have some ions, you can have some X-rays, photons and you see the response right of the reflecting beam, diffracting beam. So, different methods can be used to characterize the catalyst or to identify the surface methodology. So, we were talking about TPR, that was the one method, and the second one is TGA, thermogravimetric analysis, right. So, we have talked about this yesterday also. So, the thermogravimetric analysis, if you look at it, measures the amount and rate of change, right, something with respect to temperature and time. If you have some data and how weight changes with either temperature or time. So, you can find out very easily the kinetics also by using these operators, but in the case of catalysis this can be used to determine the temperature required for oxidation, right, the moisture present. If you want to remove the coke from the catalyst, then you can again have the heating in the stream of oxygen. So, you can get the different information. So, basically you can get weight of a material as a function of temperature or time in a controlled atmosphere, right. So, measurements are used primarily to determine the composition of material and to predict their thermal stability, may be a temperature range up to 1000 degree, 1200. So, it depends on the unit or furnace which has been used for the operation, right. So, the technique, this can characterize materials which is weight loss or gain, because sometimes if you have a precursor of the metal and when you have the oxidation or oxidizing environment, it may oxidize also. So, during heat treatment you can have the weight gain also, right. So, weight gain, so depending upon that you can find out the delta H which is related to temperature for a given weight gain. So, you can find out the enthalpy of the reaction also, right. Oxidation, dehydration. So, all these kinds of information, the temperature required for oxidation, temperature required for dehydration, decomposition of a material. So, these information can be obtained from thermogravimetric analysis, right. So, sometimes if you connect it with the mass spectrometer unit, then you can have the composition also of the product, right. So, what is the product? So, especially when you have a biomass type material and if you want to pyrolyze it and to look at different conditions of temperature, and even this can be done at pressure also, right. So, you can get the information about the product gases and you can have the catalyst also in the unit. So, kind of reactor where you have a bed of catalyst and then do the thermogravimetric analysis. So, it is a kind of micro reactor, right. You can have a different type of tubes with different catalysts and give the same stream of the reactant gas, right, and then look at the product composition through the GCMS. So, the information from the TGA, it can be of variety, right, thermal stability of the material, oxidative stability of the material, composition of multi component systems, then estimated lifetime of a product, that is the decomposition if you look at the for a product, right, decomposition kinetics of the material. So, TGA can be used for that biomass, coal conversion, right, non catalytic type reactions, you can have the kinetics as a function of temperature and time correlation. Effect of reactive or corrosive atmospheres or on different kind of materials. So, that corrosion studies can also be done with that. Moisture and volatile contaminants. So, these can also be used estimated from the TGA analysis. So, in general when we look at a catalytic activity, we are interested in determining the weight loss as a function of temperature or time on stream, right. So, then you can have the idea about the calcination temperature. If you have a hydrogen stream, you can get the idea about the reduction, and that will be similar to your TPR study, right. If the coke is deposited on the catalyst and you want to study the kinetics of the coke removal by gasification, so you can do the kinetics and the TGA operators, right. So, weight temperature profile which is helpful in establishing the procedure, right, for regenerating the catalyst and helps in determine the volatile components that is present before calcination of the catalyst. So, this kinetics of the coke removal. So, what temperature is required for regeneration of a catalyst, especially when you have a FCC type or feedstock is hydrocarbon, then large amount of coke deposits on the catalyst. So, you may need a fixed bed reactor that may have a larger life if the catalyst may last for 6 months or a year or 3 years, or if it is deactivating much faster, you can have a fluidized bed reactor, right. So, how the coke can be removed or what is the nature of that coke precursor, because when you have a temperature time profile, the different coke species will come or just gasify at different temperature. So, you can have the graphitic nature, amorphous nature or type of carbon which is deposited on the catalyst, you can have that information also. And if you take the dt, that is the differential weight loss, right, as a function of temperature or time, then you can also have the information on the endothermicity or exothermicity, whether heat is generating during the reaction, right, when you call it exothermic reaction, and when heat is required for decomposition, it is known as endothermic. So, when there is a the reaction is endothermic, right, then there will be a drop in temperature in the system, because it takes the heat, right, to have some reaction, and when the heat is generating, so you will find a rise in temperature. So, by looking that profile, you can get the idea about the endothermicity and exothermicity of the reaction. So, just as an example, what TGA can do or what information you can get from TGA. So, a calcium oxalate. So, this is just like calcium carbonate or any calcium nitrate, just to look at the decomposition profile. So, calcium oxalate. So, if you do the TGA, so there are 3 zones. So, one zone, first zone, second zone and third zone here, right. So, this is the actual profile which you will get from TGA. So, that is their weight loss as a function of temperature, and this temperature, you know what is the rate of change of temperature with time. So, dt by dt. So, basically we have two information, temperature versus time on stream. So, which is that generally you give the profile something like 10 degree Kelvin, what I was talking per minute, right, something like this. So, dt by dt a linear profile something, right, some kind of if you just take dt by dt 10. So, it is something like alpha t plus some constant, something like that, right, a constant which is. So, this information gives you weight loss as a function of temperature, where temperature may change with time if you have not maintained the isothermal condition. So, first zone is here, which is around say up to 200 degree centigrade, then second zone another weight loss which is 400 and between 400 and 550 degree, and then after 580 or 590 there is another decomposition, and that lasts up to this, and after that there is no weight loss. So, a constant line will arrive, right. So, and this is simply nothing but the weight, or if you have a derivative of that, that is which is here in terms of the percentage per minute, right, that is dW by d time, right. So, that can give you the idea about that at what time there is a maximum decrease in the weight, right, or change in weight, which is nothing but rate of change of mass per unit time, right. And if you just take it divide by per unit mass of this solid, you are getting something like rate which is related to the kinetics, right. A simple, just what I said earlier also, that dW by dt is equal to k times 1 minus alpha, which is the fraction left to the power n, simple kinetics, power law kinetics, right. So, this is the derivative of weight, that is within this you can just take the slopes, right, the temperature is related to time. So, I can take the tangent at different points and you can get the information on this weight loss, right. So, why 3 peaks now? So, you can analyze the data. So, just if you look at here, the first step, if you have the calcium oxalate, so that just removes the water, right, it is a hydrated one. So, monohydrate. So, the water is removed in the first step, right. So, rate of removal of water from the solid can be calculated, kinetics of that. And in the second step, which is somewhere near 400 degree centigrade or after that, the calcium oxalate decompose and gives calcium carbonate and carbon monoxide, right. So, this is what is the gain weight of carbon monoxide in one way, right, which forms, if you have a mass spectrometer or if you have a detector, you can measure that carbon monoxide concentration, right. and that can be related with the decrease in mass of this calcium oxalate, right, because ultimately the sample has now calcium carbonate. The kinetics of this reaction can be obtained. And third one, then further, that is about 580 590 degree centigrade, then calcium carbonate decompose and you get calcium oxide plus carbon dioxide. So, you will get carbon dioxide gas through the detector and you can measure that concentration, right. So, this is what here the weight loss is related to the mass of the gaseous product, because of it is a material balance, right. So, that is what you can write from that, either the rate of formation of carbon monoxide, rate of formation of carbon dioxide, or rate of decomposition of calcium oxalate or decomposition of calcium carbonate. So, the information, a variety of information can be obtained if you look at just a non-catalytic type of reaction or decomposition of the material. From catalytic point of view, again we get similar information, that is you have a catalyst which is precalcined, right, something like a calcium carbonate itself may be a precursor for catalyst, right, support material, calcium nitrate, it can be also a support material. Same thing for other like nickel nitrate, if you have in your catalyst precursor. So, after when you have done the initial preparation part, what you say the co-precipitation method, Sol-Gel method, wet impregnation method, right, and you have done the drying or aging for 24 hours. So, now we say that calcine it, right, where you get the definite phase edge, right. So, that is one thing. Simultaneously during that step, this the salt decompose, right, and you get the oxide precursor, right. So, that is known as pre-calcination condition. So, what is the temperature required? As I said that calcination temperature is very important, because it gives you the phase edge, right. During calcination you get different phase edge on the catalyst surface, right, and excessive calcination is not desired, because it is a kind of reaction, right, solid solid reaction, and that may happen that there may be a different kind of phase form because of the solid solid reaction or because of the interaction between the metals. So, sintering may arrive, right. So, the crystal size increase, grow in size. So, your dispersion which we talked yesterday decrease, right. So, in order to avoid those situations, you have to look at the optimum condition required for calcination, and higher the temperature, another thing that beyond calcination you are giving more energy to the system, right. So, energy consumption point of view also you have to check these things. So, this the TGA operators or TGA, by doing TGA of the pre-calcined sample you can find out the calcination temperature. So, here if you look at just we have just taken nickel cobalt, right, nickel cobalt on ceria zirconia. So, basically used for reforming of these bio oil components or methanol, ethanol. So, these kind of metals can be used for reforming reaction. Another is on nickel lanthanum oxide, aluminum oxide, which is again a composite support here, and nickel. So, these are but pre-calcined catalysts. So, this will be in the form of nitrate components, right. So, if you look at the graphs, so this is the NC, which is your nickel cobalt. So, a first one. So, this is first one. So, this is the TGA line, right. This one, the orange color line is the TGA of that nickel fresh catalyst, right. If you have something, the second one which is a NLA type lanthanum aluminum oxide, the TGA obtained is something like this one. So, this is weight loss I am talking. So, this side, right. So, weight versus temperature, and these two graphs are something like this. And for third one, which is again for fresh catalyst, the TGA line is this, a decrease in the weight, which is much more compared to these two, right. If you look at this point, so here the weight loss is very high, right. So, this third one, which is your catalyst related, which is given here NCCZ, nickel cobalt ceria zirconia. The reason is there, weight loss is that because nickel nitrate may be there, cobalt nitrate is there, right, both are decomposing, right, and the temperature for nickel nitrate may be different, cobalt nitrate may be different, but there may be a kind of overlap. So, if you look at this, the peak change here in terms of the shape, right. So, you can have one cobalt nitrate separately, you can have nickel nitrate separately, and then you check, right, at what temperature nickel nitrate decompose, what temperature this, and this should give you the combined weight loss of nickel nitrate and calcium cobalt nitrate, right. So, a combined temperature which is required for these two metal precursors for calcination you can identify from this. So, at this temperature you see that all this material have both materials have decomposed, right. So, it means around 350 or 380 may be the suitable temperature for calcination, right. So, you can go around 400 degree centigrade, and also what is the time required for complete decomposition, that information also you can get from this, right. Say 5 hour, 3 hour, because depending upon your material, amount of material, you can just do that also, right. So, that is the information which you get from the weight loss as a function of temperature. And if you do the further analysis, that is the derivative of this, right, can give you the information about the change in weight as a function of time, right, kinetic information, right, kinetics. Although for the calcination you are not much interested in getting those information, but if you need the for some kinetic reaction, you can calculate this derivative also. But from this you can find out also the exothermicity or endothermicity nature of the reaction. So, here it is decomposition, right. So, which requires the temperature for decomposition, right. So, temperature required. So, it means there will be a variation. If you look at the temperature will fall down at a certain, if you take the derivative of temperature and weight loss, right. So, drop will come if this is, so something like if you have the isothermal system, the system will go like this, right. But in between when there is heat is generating, right. So, it will go like this because temperature has risen, right, certain, although the mass of the material is of the order of microgram, right. So, that delta T will be just of the order of 1 degree or 2 degree, right, depends what is the delta H for that. So, but you will see some kind of deflection if you have temperature profile as a function of time here, right. So, actually what you have given is T say 10 degree ramp. So, you could have gotten some a linear profile, right. So, but if you look at that profile, then there will be something when there is a decomposition, weight loss or weight gain. So, you will have something like this which talks that it is exothermic in nature, right. And if there is something which profile which goes down like this, it means this is endothermic, because there is a drop in temperature, right. So, when you see that there is a drop in temperature, so this simply gives the idea about the endothermic, because the system takes heat during the further heat for decomposition. So, temperature will fall down. So, these informations can be obtained whether endothermic or exothermic nature of decomposition you can get. So, combustion, when you have coal combustion, on where you have the regeneration of the carbon from the catalyst. So, that time you will find that there is a heat generation, because the combustion reaction is exothermic, right. So, this is what the information you get from TPR, TPD and then TGA. So, I told that heat based system, right, you heat the sample, right, and you get the information. Now, another term which we are talking about, photons, right, or some energy source which may be your primary energy beam, and then you look at the diffraction, right. So, last time I was talking about that the information what you can get from the different catalyst system. If you just look at, I can just have the slide something like this. So, this I will take little later, not for this, but generally for a primary electron beam, right, or X-rays, the principle is similar. The X-ray has the wavelength of 100 angstrom of the order of that, right. So, it means it will cover a wider surface, something like that. But when the electron beam, if you see, it has the wavelength which is less than 1 angstrom. So, it can give you the atomic information, right. So, right now what I want to inform that whenever there is a primary beam which strikes the solid surface, then there will be some kind of diffraction, because it will depend on the nature of the solid, soft material, hard material, right. So, that is the material science here, right. The platinum, a hard material, right, but if you have alumina, soft material. So, but in any kind of when depending upon this energy, right. So, whether it may be of the order of 100 kilo electron volt or it may be of the order of 400, it requires a vacuum also. The only thing that you may not get the information at actual reaction condition, right, that is the only drawback of these methods, because actually your reaction may be at say 500 degree centigrade and 20 atmosphere, but these systems generally work at high vacuum, right. So, but to have the information about the surface not at the actual reaction condition, right, or how does the electron emits the surface of from a catalyst, right, of a catalyst, then you have the different information which can be correlated to the actual reaction condition. Right. So, that is the idea in the catalytic activity, that we were talking that transition metals are good, why they are good. So, I want to look at, give you the certain information on that, which is based on your electrons theory, right, atoms, right, how they are on a metal electrons, and when you have the bombardment, then how these electrons emit, right. So, this primary electron beam, it strikes the surface. So, there can be some back scattered electrons, right. This is back scattered electron, what you call secondary electrons, and also known as Auger electron, right. So, they are slightly weaker in energy, but the information from this is also very useful information you can get, that is known as Auger electron microscopy. We will talk on that later. And the same, there may be some kind of X-rays, right, which reflects from the surface, there may be photons, and if the material is soft, then there is a kind of diffraction also, right. So, depending upon the beam energy. So, it can be a diffracted electron. So, that principally used for transmission electron micrograph. So, you measure the property of the diffracted electron, right. If it can be some kind of loss electrons, right, which have just from here the metal have the, because it is a kind of atom layers. So, from which layer of the surface, top layer, middle layer. So, that will depend on the beam energy, and it goes in depth, like when we talk XPS, X-ray photospectroscopy, right, that goes. So, depending upon the energy of that beam in the X-ray photospectroscopy, that goes up to the in depth. So, you can have in depth analysis of the spectra, like say carbon when deposits, whether it is only on the top layer or in different layers, right. Same thing electronic, the metal composition can be determined, size of the crystal can be determined, because these informations are at atomic level. So, that is why this is for electron microscopy, not for the X-ray basically, right, because the electrons, they have the wavelength of the order of less than 1 angstrom, right. So, you can get the information about the atomic level, right. So, I will come back to this again later, but right now just my idea here is that when some energy source strike the surface, that there will be a diffraction, there will be some transmission, and we are interested in looking at properties of those reflected, transmitted, right, energy secondary electrons, and that is correlated with the property, because something in the atom you have the sp bands, right, and you have a d orbitals, d band, right. So, based on those spd band, you get a certain kind of electronic property, right, and that is related to your catalytic activity, because you are talking in terms of Cammie-Jobson. We need a kind of Cammie-Jobson between a gas molecule and the atom, right, and that will depend on the actual property, that when the gas molecule, what is the electronic configuration of this metal, and then how do they contact. So, orientation also becomes very important, right, in terms of having a certain catalytic activity. So, in this case of X-ray, the diffraction occurs in the elastic scattering of X-ray photons, right, by the atoms in a periodic lattice. So, it is nothing but a structural surface on which atoms are arranged, and some X-ray beam which has a roughly wavelength 100 angstrom, it strikes on the surface, right. So, the monochromatic X-rays that are in the phase gives the constructive inference. So, this is what the information you get from the X-ray is, nothing but beam strikes, and then diffraction is there, reflection is there, right. So, we are just measuring it based on the Bragg's law, that is just basically n lambda, right. You know the lambda is equal to 2d sin of theta, that is the Bragg's law, right. So, this is written here, that this X-ray diffraction pattern, right, used to identify the crystalline phases inside the catalyst by means of lattice structural parameter, right. So, the arrangement of the atoms on this surface, right, metals are how they are arranged, and when you have the X-ray beam, right, and that reflects. So, there can be different kind of X-ray sources, right, of different energy, beam energy, and then you see the at what angle there is a diffraction, right. So, it may be up to a certain depth. So, and it may be from the surface, that depends on the beam energy. So, this is what we are interested here in lattice structural parameter. And if you just go further in details, then you can get the crystal size also, right, because that is also related to a peak width, right. When you have the X-ray profiles, then we talk either in terms of the intensity of the peak, right, or we talk the peak width at different diffraction angles, right. So, it is something like that, a atom strikes the beam and then diffracts, right, and similarly in the different layers this will happen. So, here again the beam diffracts, right. So, this is what we are talking, the angle of diffraction, because that may change depending upon the right surface and the orientation. So, you will have different lattice planes, right. So, sometimes we refer in terms of 1 1 1 1 0 0. So, HKL, the planes on which the beam strikes and diffraction in what phase or what plane that from which the diffraction has taken place. So, nickel you may see 1 1 1 some and 1 0 0, right, which is just representing the planes x y z planes, right. So, Bragg's law all of you know. So, n lambda is 2 d sin of theta, but d is known as interplanar distance, right, that is distance between two lattice, and this is the property of a phase, definite phase. So, this will change from different phase to phase, right. Lambda is the wavelength of radiation of the X-ray. So, this is a source beam. So, suppose you have generally most of the time either you have copper potassium alpha radiation or magnesium potassium alpha, right. So, this copper potassium has roughly a wavelength of 1.5 angstrom, right. So, this depending upon the source you can have this value which is fixed for a beam or for a source, right. D is the distance between the lattice planes, that is the property of the crystal, right, and theta is angle between the incoming X-rays and the normal to the reflecting plane, right. So, that is important because at different theta value you get the different diffraction, right, and n is an integer. So, first, second, third like that. So, if you know this angle 2 theta, because you have given the beam interaction and then you are just measuring the intensity of the different diffracted beams, right. So, reflected beams which comes from the surface. So, under which the interfering X-rays leave the crystal, the Bragg's equation gives the corresponding lattice spacing which are characteristic of a particular compound. So, that is what the discussion, that if you know this lambda, if you know this theta, then you can find out the d value, right, and d value is related to the material and which are nowadays available in the software. JCPDS software is one where you can have the information that this d value which is of the order of angstrom is for which kind of phase, right. So, X-ray diffraction pattern, it gives you a very useful information in one way. You can characterize the catalyst, then diffraction patterns are mainly used to identify the crystallographic phase and their size in the surface of the catalyst. So, generally the crystal size, what you get in XRD, so you have here 2 theta and that depends on the some preliminary survey that what range of 2 theta is required. So, it can be say 10 degree to something like 70 degree, but if you see that you need sometimes a smaller angle. So, you need a small angle X-ray diffraction also when you need the diffraction patterns at smaller angles, right. So, then you have some this side you have some what you call orbit unit and intensity, right. So, this so suppose if you have done this analysis, so you will have a diffraction pattern something like this. So, if the material is crystalline, then you will get these peaks, right, because the phases are formed. If the material is not crystalline, then there will not be any peak. So, you will get just like line like this. So, this is for a non crystalline material, right, but for a crystalline material you get peak like that. So, at different 2 theta value. So, this is your 2 theta value like this. So, you can identify from the calculation which is your lambda is equal to 2 d sin of theta. So, you are getting this d value, right. So, if this is 2 theta value, right. So, lambda is known to you. So, this will tell you that this is which phase. Suppose you have calcium aluminate, so it can have CaA, it can have 12 CaA, 7U2 what I said earlier, right. So, you can have the information about this phase, right. So, and also simultaneously the intensity, right, some relative number. Suppose this is the highest peak. So, I can make this 100 number, right, some orbit number, and then the intensity of rest of the peak can be defined in terms of a ratio of the peak heights, right. So, this height is highest one. So, this can be numbered intensity 100 and the other peak intensities can be determined based on this. So, it can be something like I over I 0, some orbit unit, right. And another useful information which you get from this is your that this peak width gives you the indication about the crystal size. So, crystal size right, which is sometimes represented by L is equal to k lambda over beta cos of theta, something like this, right. So, this is a constant, all the this k is roughly 1, it is a property basically 1, right. So, beta is the peak width f half height, right. So, it means if at a given angle of diffraction 2 theta, this is the total height. So, this is something like here beta is the peak width at half height in radian units, right. So, this can be calculated, and if wider the peak, because beta is inversely proportional to peak width. So, if wider the peak, then you can have the information about the crystal size. So, wider peak means a smaller crystal, right. So, you can get the crystal size also from this, and that can be compared from your Kamijo-Opson study, right. So, this is another useful information which you can get from the X-ray diffraction pattern. So, generally as I discussed that X-ray irradiate the sample surface hitting the core electrons of the atom. So, now core electrons is another term which I will just talk little later. So, that is important because we talk core electron, not the outermost electron. So, which is related to something like Fermi level. So, we have to just look at the atomic level and the structure of an atom, right, how the electrons sp what we talk work function, Fermi level, vacuum level. So, these are related from which the electrons are emitted, right. So, outermost core may not give you the good information because it is far away, right, from the nucleus. The atoms which are closer or electrons which are closer to nuclei, they provide you the better information because that is specific for a given material, right. So, most of the time we look at that, and that is what it is a core electron of the atom where the X-rays are hitting, right, and you need the information from the core electrons, right. So, X-rays penetrate to the sample to a depth on the order of a micrometer. So, that depends on the intensity of X-ray radiation, wavelength of that radiation or energy provided, right. So, useful electron signal is obtained only from a depth of around 10 to 100 angstrom on the surface. So, that is so X-ray basically scans the surface and then during the scanning it identifies that whatever the different theta angle, whatever the diffraction, and it just talk on that a different diffraction angle, and then it talks about the crystal because crystal has a definite shape, right. So, from where the diffraction takes place. If it is not crystal X-ray, you will not get any peak, no diffraction will come, right. So, X-ray sources generally they produce photons, right, with certain energy. So, that is H nu type of energy which you get, right. So, just like magnesium potassium photon if I was talking. So, that has energy of roughly say 1.25 kilo electron volt, right, and whereas aluminum potassium photon it has energy of 1.486 kilo electron volt. So, different type of source, right, it has the different source of energy, right. So, that is your H nu type whatever the nu is the frequencies, right. So, that can be used. So, normally the sample is radiated with photons, right, of a single energy. So, that what we call monochromatic energy source, right. So, single energy like magnesium potassium alpha, aluminum potassium, copper potassium, right. So, it is known as mono energetic X-ray beam. So, now just that in order to look at these electrons we have to just look at the atom, right. So, you know the atom has an electron with different binding energy. So, binding energy is different because we are talking now in terms of the energy which is required and electron will leave the surface. So, binding energy is different, depends on the kinetic energy, it depends on the work function, it depends on the potential, that is the work potential of the instrument also, right. So, every atom will have, if you look at the electrons, they will have different binding energy and each of which has some probability of being ejected. So, they will leave the metal, right, when the energy beam has struck on that. So, series of electrons, they may have different kinetic energy and they are emitted from the atom. So, we are basically what doing, the measuring the kinetic energy of those beam, right. The photoelectron spectroscopy, that is another one, XPS, right, which we will talk later. The number of electron emitted per second. So, that is something related to the intensity, right. The number of electron emitted per second, the known as intensity, that is measured as a function of kinetic energy of the electron, right. So, when a soft X-ray beam is used as the stimulant, it is known as X-ray photoelectron spectroscopy. So, that is the XPS is different instrument which relates the binding energy, right, that is the kinetic energy or binding energy, and then it gives the composition of the metal throughout, right. So, the composition can be determined, in-depth analysis can be determined, right. You can get the bonding, type of bonding also. So, a variety of information can be obtained by using this X-ray photo spectroscopy, which is based on the binding energy. So, all of you know this. So, just to recall the things, that every atom, it has some proton, neutron and then electrons, right, and they are just like, this is what I am talking, core electron, because it is closer to the nuclei, right. So, this electron, the energy beam strikes here. So, we are looking at the reflection of this electron. So, like this, this is the source of energy, X-ray, right, and it strikes here and then it leaves some free electron here, right, and here the valence electron which are on the outermost side. So, they are free to move, in fact, right, they are just binded, but free to move anywhere. So, very mobile. So, these are known as valence electron, right. So, core electrons respond very well to the X-ray energy. So, that is why the information but is required, important information is from the core electron, right. So, the valence band, conduction band, right, which is the semiconductor materials, when you see the catalytic property, the metals, right. So, the two regions of the energetic states, that is what we are talking in this form of core energy and X-ray strikes. So, you look the information, or we need the information in terms of the core electron, right. So, valence band and conduction band. So, there are two type of energy, that is the semiconductors, when you say, right, they need a certain kind of energy and then they have the gap, right, and that can provide the electronic activity, just like in titanium dioxide, right. For UV, when you have a UV source, it can activate as a catalytic activity, right, but otherwise it is no more good as a catalyst, right. So, that is a semiconductor material. So, you need a kind of mobile electrons, or these are also known as positive holes, right. So, a gap. So, related to Fermi level, right. So, Fermi level, it is a potential energy of the electron that is characterized by the Fermi level, which corresponds to the electrochemical potential of the electron and the electron holes. So, generally Fermi level, right, above Fermi level the energy is minimum basically, right, and below that the energy is maximum. So, it is a gap between, right. So, that, so what we call work function, as I discussed, I was talking. So, that is we are measuring it above the Fermi level, right, that is the vacuum level energy minus the Fermi level, that is the kind of work function, which is the amount of energy which is required to release an electron, right. So, that is important, Fermi level is important, and this gap will be different in different methods. So, if I just show you, which you must have read earlier. So, this is the kind of structure of a metal or electron atomic structure in the metal atom, right. So, this is a core level like here, right. So, core, you have different levels, core level 2, core level 1, and which is based on the different their SPD bands, right. So, core level 1, core level 2, so that depends on the total number of electrons which are distributed, right. And so, and this is your the SP band here, which is the electrons are just free and they are just filled here, right. So, and then the Fermi level, this is your Fermi level, right. So, here it is the energy is highest here in this side, and here it is the vacuum level which has the now electron are free to move, right, in this zone, right, what I was talking outermost core of that, and in between this the difference of this is your work function. So, if you look at here, it is something related to your ionization energy again, right, the energy required to to remove the electron from the outermost core, and that is nothing but ionization energy to create an ion, right. So, that is a free atom here when you have this kind of, this is a kind of adsorbed atom. So, when this is a metal, this is adsorbed atom. So, energy band shifts, right, when something, because it is a Kami-Jobson which is related to the electron transformation, right. So, that is what the structure is related here, and that is the Fermi level. So, position of Fermi level is very important. So, this shifts moves, right. So, position of Fermi level indicates the number density of electron in the band model, right. So, SP band is below the Fermi level, right, where the all the bands are filled by the electrons, right. They are just, so it's the energy is associated to that band, right, and above that when I am talking vacuum level, the energy is the electrons are free to move, right, that is minimum energy, and the Fermi level where the electrons and below that high energy, right, and above that the electrons have the low energy, right. So, work function, the energy required to transport an electron from the edge of a Fermi level into a vacuum, right. So, after that the electrons are free to move, right, that corresponds to the work function, right. So, difference of this, that is the vacuum energy minus the Fermi level energy is your the work function. So, that is the energy you need, right. So, electron has to move from the core, right. So, for d block metal, if you say, because most of the d block metals, the work function is roughly 4 electron volt. So, low number if you look at in terms of the high h nu energy, which is of the order of kilo electron volt, right, and therefore, this is in the ultraviolet range, right. Lower the Fermi level, stronger the adsorption. So, your Kami-Jobson, whether it is strong metal support interaction what we are talking, right, or the gas molecule adsorbs strongly on the metal, that is related to the Fermi level. So, if Fermi level is on a lower side, right, your Kami-Jobson will be strong, stronger the adsorption, right. So, you have to tune it, in fact, the metal selection, because this is for a given metal, the electrons are distributed in their cores, right, S, P, D, K cell, what you see defined in that L cell. So, the electrons are distributed. So, you have when you select the metal for a given reaction, the adsorption should not be very strong, adsorption should not be very weak also. So, this is what are related to the electronic theory or electron, how they are distributed in the cores or cells. So, work function we have talked, it is the minimum energy needed to remove an electron from a solid and take it infinitely far away to 0 potential energy. So, vacuum level, right. So, vacuum level has the minimum energy 0. So, electron has to be taken from the Fermi level and transfer it to the vacuum level. So, that is your work function. So, weakest bound electron in a solid are at the Fermi level, right, because below that their energy is high, right. So, vacuum level is the minimum energy that an electron has that is not bound, but free to move in any direction. So, the definition I already discussed, right. So, that is you need to see vacuum level, work function, which are the property of the atom, right, of a metal. So, work function definition is energy difference between vacuum level and Fermi level, right. So, Fermi level is on a lower side, right, that what I said, the Fermi level is on a lower side, then work function will be high, right. So, that is the that is high, though it means you need high energy, right, to release the electron from the core. So, the same what discussion has been made is shown here now. So, this is your vacuum level, right, and this is your lowest energy state. So, the what we are talking the cores, right, core electron, and this is the work function which we have defined. So, this is your Fermi level. So, this is your work function, right, phi, right. So, vacuum level minus Fermi level, and this is the binding energy. So, I told that the core electrons are required. So, binding energy gives you the idea about that how strongly this core electron is attached to a nucleus, right, or that is the what is the energy intensity between the nucleus and the core electron, because you have to relieve that electron for catalytic activity, right. So, that is related to the binding energy. So, when you have the X-ray photospectroscopy, you just look at that. So, binding energy we are measuring in fact which is the property of a material now, right, by giving a kind of kinetic energy, right. So, this Fermi level, vacuum level, right, difference is the work function, and from the core when the electrons are relieved. So, that is the nothing but how the electrons are attached to a nuclei, and that is your the binding energy, right. So, at absolute 0 Kelvin, the electron fill from the lowest energy states up, right. When electron occupy up to this level, the natural neutral solid is in its ground state. So, that is the normal condition when they are neutral, right. So, that is at 0 degree Kelvin you won't see any the electrons everything, that is the stagnant position, right. So, there is no, so that is the lowest energy state, right. Electron fill from the lowest energy state. When the electron occupies up to this level, the neutral solid in its ground state, right, when there is no activity. So, why core electron? I have already just discussed this, but the electron near a Fermi level, right, is far from the nuclei, right, that is the one thing. So, core level is below the Fermi level, right. So, moving in different directions all over at the place. So, this may not give you a very useful information, right, because at the Fermi level they are free to move up, that is the work function I told, and then the vacuum level, right. So, lowest energy is in vacuum level, and below Fermi level there is a energy, right. So, this may not give you the useful information about any single atom, right. So, Fermi level may not give you the any useful information, right, but if you have the core electron, you get the useful information, right, because they are binded to the nuclei, right. So, Fermi level is the highest energy level occupied by an electron in a neutral solid at absolute 0 Kelvin, that is what the discussed, right. So, electron binding energy is calculated with respect to the Fermi level. So, that is from core to the Fermi level, which is shown here. Fermi level, this is core, and that is really important. Here the electrons are free to move in between, right. So, they may not give the useful information, but for a given atom the or given metal, the atoms are attached to a nucleus, right, the proton, neutron and then electrons, right. So, it means what is those kind of energy when the electron is released and comes to a Fermi level, right. So, that is important. So, that is your binding energy basically, right. So, that is maybe giving you the useful information, because it is related to the number of proton in the nucleus. So, core electrons are local close to the nucleus, right. So, locally they are close to the nucleus and having a binding energy characteristic of their particular element. So, that is why the core electrons are useful, and they have higher probability of matching with the energies of whatever the alpha potassium or magnesium potassium, which is used for the X-ray, right, analysis. So, valence electron, core electron, atom. So, we are looking something like here in this course. So, when a beam strikes the surface, as I said before also, that these are your just the X-rays, which is shown by dark arrows here. So, the different X-ray beams right here. So, these all are your X-ray beams here, which strikes. So, it can strike on the surface, top surface. So, this is your top layer, right, outer surface, this one is your outer surface, and this is your inner surface of a metal depth, right. So, electrons, this is which the electrons or X-ray which have gone up to the depth, right, they may leave the electron and they may collide, right. So, these are with collision. So, with the these are the arrangement of the inner surface, right. So, they are colliding with different surface. So, energy will the energy will decrease, because they are colliding with the substrate, right, and really the part of the energy will be lost, right. So, this is what the in depth analysis what you are getting. right, and sometimes this output energy may not be a significant number to give you any information, right. The electrons, again the X-ray which have gone to this, they may come out, but without collision, unlike here, right. So, this is the another type of the reflected beam. So, this is electron lower layer with collisions like this, but here the number of collisions may be less or may not be in this zone, second layer or bottom layer, right. The top layers, this is the electron which have released, right, from the top layer, right. So, these all are the X-rays which strikes on the top surface and then relieves here. So, whatever the analysis you can get, that is the phases which have been formed based on the diffraction angle or the whatever the intensity of these radiation electron, secondary electron. When you have the XPS, the information can be obtained in terms of the binding energy of that, right, electron. So, different type of information can be obtained from primary, secondary or the energy beams which I saw, Auger electrons, right, or the diffracted electrons. So, if you have, but when you X-ray, then you have just the surface information, right, in terms of the crystallographic nature, crystal structure, right. So, binding energy already has been defined. So, it is the characteristic of the core electron, right, for each element. So, this will be differing from element to element, right. The binding energy is determined by attraction of the electron to the nucleus, right. If an electron with an energy x is pulled away from the nucleus, the attraction between electron and the nucleus decrease and the binding energy decrease, right. So, this is basically when you do the X-ray photospectroscopy, you get more useful information from that, right, that from core the electron released, right, and you calculate its binding energy and which is property of the material or metal, right. So, that gives you very important information in terms of the crystals, in terms of the concentration of the metal, because different concentration metal will, different type of metal will have different binding energy, and nature of the spectra, Koch spectra also, that is monolayer, multi-layer growth of the carbon materials, right. So, that information can be obtained from this. So, now there will be a point when the electron will be free of the nucleus, when you have the given the binding energy, right, it increase. So, it will release the surface of the atom, right. So, that is what shown here. So, this is the point of zero energy attraction between electron and the nucleus here at this point, if you look at, right, and the electron is free of the atom, which is this electron, right. So, here this is, these electrons are attracted to the proton with certain binding energy x. So, all these are attached to the proton here. So, there is a kind of force between the core and the nuclei, right. So, you have to give certain amount of energy, and that is what the principle of your X-ray photospectroscopy. So, with the X-ray versus electron beam, as I said, the in terms of the surface scanning or a point to point analysis, that is another useful information. Both are important, right, both gives the give the information about the surface, right, but depending upon the energy or intensity or the wavelength, right. So, X-ray hit all sample area simultaneously, permitting data acquisition that will give an idea of the average composition of the whole surface, right. Just like the when you do the energy dispersive X-ray analysis, you get the analysis only at the average localized point, right, not the throughout the sample. So, if you look at the composition of the metal, so you have to scan the surface point wise at different location, right, then you can get the more useful information, right. So, because it hits the sample uniformly, right. So, only the localized information can be obtained when you look at the composition, chemical composition, but when you look at crystal structure, then it is good, right. Electron beam, because it is a wavelength is 1 angstrom, less than 1 angstrom what I said, it can be focused on a particular area localized, right, of the sample to determine the composition of selected area of the sample surface. So, your scanning electron micrograph, transmission electron micrograph, right. So, they are for a localized points, right. So, you get the information of that surface at the given sample, for the given sample for a given local points, right. So, again there may be, so you have to take the average throughout the surface, right. If you want to use the say number of atoms, number of metals, particle size, then you have to just take the average throughout the surface and then determine that particle size, right. the equation for energy, that is the kinetic energy which is related to h nu, the energy of the photons, right, minus the binding energy and minus the work function, work potential rather, or work function, right. So, because the energy needed to get an electron out from the surface of the solid, right. So, the kinetic energy is equal to h nu minus binding energy minus the work function. So, kinetic energy is known because it is output intensity, you can measure that, right, or depending upon the source and the reflection beam, right. H nu is the input energy source, so it is also known. Binding energy is to be calculated and work function is the property of the metal. So, that can also be determined, just as I said 4 electron volt for most of the, right, metals surfaces. So, kinetic energy that is measured in the X-ray spectrometer. So, this is the, right. H nu is the photon energy from the X-ray source, which is controlled one, right, monochromatic energy. Phi spectrometer work function. So, it is few in electron volt, right. It gets more complicated because the material in the instrument will affect it. So, generally 4 electron volt is the phi, and this is found generally by calibration because it is for instrument, right, and binding energy is unknown variable. So, this can be determined by using this information. Now, if you look at the metals, right. So, metals normally have a narrow d band. So, I was talking just about the d band theory, basically this is, right. So, metals, all the metals, they have narrow d band, right. The catalytic properties rather are strongly influenced by the occupational density of the electron in this band. So, how many electrons are available in that d band, that is what we are talking for the selection. The transition metals are good, right. So, unpaired d electrons in the d band, right. So, that is very important in this, right, in this band. So, d band, S and p bands, as I said, that they have the sufficient electrons available and they are always filled in that, right. But d band is one which is the number of unpaired electrons in the d band, that gives the kind of catalytic activity. So, in many cases if you look at, the direct relationship has been found between the catalytic activity of transition metals and the electronic properties of the unfilled d band. So, that is related to the catalytic activity, right. So, it means your d band theory is very important, d band model, when you look at why copper, why nickel, why cobalt, why rhodium, why ruthenium, right. They have been selected, right, as a catalyst, that is the first thing, right. And then when you select them, right, the volcanoplate what we were talking initially, right, when you select them for which kind of reaction, right. So, for a given reaction you say that for hydrogenation nickel is good, platinum is good, right. So, but what is the basis of selection of a metal, right. So, that becomes important when you look at the electronic structure of that metal, right. So, the principle remains whether these principles what we are talking XRD, SEM, TEM, right, or XPS. So, that is for characterization, right. But the fundamentals for the catalytic reaction it remains the same, right. That is, we are selecting that in when there is a reaction they will emit a kind of electron, right, and how strongly they are adsorbed on the surface, right, or how weakly they are adsorbed, depending upon these two situations there will be a kind of reaction, and that is the theory, or that is the principle behind transformation of that adsorbed species into a product species, right. So, that is what the importance of the d band, right, and that is based on the electronic theory, or what you say the total the structure of that metal and electron, right. So, there may be a different theory for the catalytic activity, but this is one, right. So, the main group element, right, with their s bands are typically electron donors and form strong bond with the electron acceptors, right. So, we talk acidity, basicity. So, I will continue this next time.